Hello again, everyone. This is Mr. V. Hill, and today we're going to be talking about graphing rational functions. And this is, of course, the last video of the year. Hooray! Anyways, when we're graphing these rational functions, there's basically three things we need to take care of before we start graphing. The first one is we need to identify the domain restrictions. That's going to be where the denominator happens to be 0. We need to identify whether those domain restrictions are going to lead to removable discontinuities or infinite discontinuities. And we've already talked about this a little bit before, but the removable discontinuities basically means there's going to be a hole in the graph. Whereas the infinite discontinuities are going to lead us to a vertical asymptote. And we've talked about this before again. Vertical asymptote is just a vertical line, and the graph of the rational function is just going to get closer and closer and closer to that vertical line without ever actually touching it. After we look at the domain restrictions, we then need to analyze what's going to happen near those vertical asymptotes. They're infinite discontinuities because basically the y values on the graph are going to be either blowing up to positive infinity or negative infinity. So the y's are either going to go positive infinity or negative infinity, depending upon whether you need to figure out whether the denominator is going to be positive or negative. They're going to be really small numbers, but we need to know whether they're positive small numbers or negative small numbers. We'll see that with an example in just a little bit. The third thing is we need to analyze the end behavior, meaning what's going to happen as the x's get really big or as the x's get really small. So what happens to y as x is going off to either positive infinity or negative infinity. So first off, let's just look at a pretty simple example here. Y is equal to x squared minus 4 over x minus 2. And so obviously right away we know that there is going to be a discontinuity when x is 2, because 2 minus 2 is 0 and you can't divide by 0. But we need to know whether it's going to give us a whole or a vertical asymptote. So right away we know that x cannot equal 2. But then if we factor this numerator, of course this is the difference of squares. So this whole thing is actually equal to y equals x plus 2 times x minus 2 on top. And we still have this x minus 2 on bottom. And so these factors right here, the x minus 2 on top and the x minus 2 on bottom, those will cancel each other out. So really anywhere except when x is equal to 2, these things cancel each other out. So this x equals negative 2, or when x cannot be negative 2, or excuse me, cannot be 2, that is a removable discontinuity, meaning there's just a hole in the graph there. And everywhere else, this function is going to behave just like x plus 2. So really all we got to do here is, let's just do a quick sketch. We know y is going to be equal to x plus 2. That's just a line with a y-intercept of 2 and a slope of 1. It's going to look just like that, except when x equals 2, we have a hole in the graph. And we can even check that with our calculator just to verify that our thinking was correct. So just go into y equals, and remember with the calculator you have to put the numerator and denominator in parentheses. So our numerator is x squared minus 4 divided by the denominator of x minus 2. And if we graph that, yep, sure enough, it's looking just like a straight line with a y-intercept of 2 and a slope of 1. We can't see the hole right now though. What we're going to need to do to see that is we're going to go zoom decimal, so they get a 1 pixel for each tenth. And we can't quite see it, so we're just going to double each of the maxes and mins on the x and on the y. And now we'll have a pixel every 2/10 or 1/5. And there we go. Now we can see the hole in the graph right there. So it looks exactly like what we drew over here. But notice this one did not have any vertical asymptotes or any infinite discontinuities, so this one was pretty simple. Let's look at a little bit more complicated example. Now we have a quadratic on top and a quadratic on bottom. So in order to see what the discontinuities are, first we're going to factor both the numerator and the denominator. And we know how to do that. The numerator is going to factor as, let's see here, two numbers that will multiply together to give us -6, but add together to give us a +1. That would be 3 and -2. So this would be x plus 3 times x minus 2 on top. And on bottom, well, two numbers that multiply together to give us 3, but add together to give us 4. That's, of course, 3 and 1. So this would be x plus 3 times x plus 1 on bottom. So the values that x cannot be would be a -3 for this factor and a -1 for this factor. But notice we also have a factor of x plus 3 in the numerator. So everywhere except where x is equal to -3, these two factors will cancel each other out. So this -3 is going to give us a hole in the graph, but this x plus 1, that doesn't cancel out with anything else. So that x plus 1 leads to an infinite discontinuity or a vertical asymptote. Okay, so we've identified our domain restrictions, and we know that this one is going to give us a hole in the graph, and this one is going to give us a vertical asymptote. So now we need to see what's going to happen near that vertical asymptote. So first off, let's just kind of draw a little sketch here to kind of see where we're going with this. Of course, we have our x-axis, y-axis, and our vertical asymptote is at x equals -1. So that's a vertical line right there. I'm just going to do a little dotted line showing that vertical asymptote here. Now, as the x's are getting closer and closer to that asymptote from the left, well, we just kind of look at what's going to happen in here. Really, we're not anywhere near that x equals -3. We're not near the hole. So we know over here there's going to be a hole in the graph wherever x equals -3. But as we're coming in here, now the function is going to behave just like these two factors over here. The x plus 3's cancel each other out. So as x is approaching -1, y is going to be approaching x minus 2, or -1 minus 2, over -1 plus 1. It's not going to actually get there because x is just approaching -1. It's not actually equal to it. But so that thing is going to be getting closer and closer to, well, the top is going to be -3, and the bottom is going to be approaching 0. But notice here, it's approaching 0 from the left here. So it's, the x is going to be getting closer and closer to -1, but over here from the left. So x is going to be getting, like, I don't know, -1 plus 0.1. So -1.1 plus 1 would be -0.1. So really, this right here is going to be a small negative number as x is approaching -1 from the left, which means that y is going to be approaching a -3 divided by a really, really, really small negative number. The negative divided by a negative is going to be a positive, and any constant divided by something getting really, really, really small is going to be getting really, really, really big. So this thing is going to be approaching positive infinity as x is getting closer and closer to -1. So as the graph is coming in this way, from the left, it's going to be shooting off vertically toward positive infinity, or up. Now, what's going to happen as x is approaching -1 from the right? Here, now, again, y is going to be approaching just these two factors because the x plus 3's cancel out. It's still going to be -1 minus 2 on top, or something close to that, and -1 plus 1 on the bottom. So it's still going to be approaching -3 over 0. But now, as x is coming in from the right, the x is going to be a little bit bigger than -1. Something a little bit bigger than -1 plus 1, that's going to be a positive number. So this thing is really, on bottom, it's not 0, it's actually just going to be a small, 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 small positive number. So now we have a negative on top and a positive on bottom, so the whole result is going to be negative. But now, -3 divided by a really small thing is going to be a really big thing. And now it's going to be negative, so y is going to approach negative infinity. Meaning over here, the graph is going to be coming in and then shooting down alongside that vertical asymptote. Okay. Now, as far as the end behavior goes, we want to know what's happening as x goes to positive and negative infinity. So, as x goes to positive or negative infinity, we're really looking at, again, y is equal to x minus 2 over x plus 1. The x plus 3's cancel out. So y is going to be approaching, well, kind of infinity minus 2 over infinity plus 1. Or really just some gigantic number, subtract 2 from that, and divide the result by the same gigantic number, but add 1 to it. So really, if you think about that, these big gigantic number divided by itself, but really something just a little bit less than that, divided by something a little bit more than that, this minus 2 and plus 1 don't really matter in the big scheme of things. 5 billion minus 2 divided by 5 billion plus 1, that's going to be really, really, really close to 1. So y is going to be getting closer and closer and closer to just 1 as x is getting huge, either positively or negatively. Doesn't really matter. What that means is that there's going to be a horizontal asymptote there at y equals 1. So you can put that in as well. So there's my horizontal asymptote. So basically what we're saying here is as x is getting closer and closer to -1, we're going to shoot off to positive infinity that way. But now we're going to get closer and closer to y equals 1 as x gets really small. We're going towards negative infinity. Same thing over here, but except now we're going to be shooting off towards negative infinity, and then the graph will be getting closer and closer to the horizontal asymptote of y equals 1 in that direction. Let's check in our calculator really quick just to see if it's giving us something similar to that. So again, y equals, let's clear this guy out, and now we're graphing x squared plus x minus 6, that's our numerator, and we're dividing by x squared plus 4x plus 3 on bottom. And let's just do a zoom standard here, regular -10 to 10. And there we see it. And this is just a regular old hyperbola. The vertical asymptote is at x equals -1. The horizontal asymptote is at y equals 1. And we see it shooting off towards positive infinity as we get in, coming in towards that vertical asymptote from the left, and shooting off to negative infinity as we approach from the right. Kind of neat. Let's try one more example where we see a little bit more bizarre behavior in these functions. And so example 3 here, we have y is equal to x squared minus x minus 6 on top and x plus 3 on bottom. So it's a quadratic divided by a linear. Now, obviously, x cannot be negative 3. But let's see if it's going to be a vertical asymptote or a whole. So if we factor the numerator, we have y is equal to, two numbers that'll work. We need to multiply together to give us negative 6, but add together to give us negative 1. That's going to be negative 3 and positive 2. So the numerator is x minus 3 times x plus 2, all divided by the denominator of x plus 3. Goofy looking 3 there, sorry. But we see that it's not going to cancel out here because we have x minus 3 on top, not x plus 3. So x cannot be negative 3, and that's going to give us a vertical asymptote. Okay. Now let's look at what's going to happen near that vertical asymptote. So near x equals negative 3, as x approaches negative 3 from the left, the y is going to be going to, well, if we plug in negative 3 here for x, it's going to be negative 3 squared. Don't forget your parentheses around that. Minus negative 3 minus 6 on top. And then negative 3 plus 3 on bottom. Or negative 3 squared would be positive 9 minus a negative, that's adding 3, that's 12, minus 6, so this is going to be 6 on top and 0 on bottom. But remember, x is going to negative 3 from the left. So really we're not actually putting in a negative 3 here, we're putting in something a little bit less than negative 3. It's like negative 3.1. So if we add that to 3, we're going to get a really small number, but also this is going to be a small negative number. So y is actually going to be approaching 6 divided by 0 is like infinity, but it's the negative number, so 6 divided by a negative, really tiny number, so there's going to be negative infinity. Okay. Now, as x approaches negative 3 from the right, again, y is going to be approaching the same exact thing, 6 divided by 0, but now, if x is just to the right of negative 3, meaning like negative 2.9, this number on bottom isn't really going to be 0, it's just going to be a small positive number. Okay. Or 6 divided by a small number, that's going to be a positive number, but it's going to be huge because we're dividing by something really tiny. So y is going to approach positive infinity as we're coming in from the right. Now, before we even go in and try to look at that, we do kind of need to look at the end behavior here. So the end behavior, we need to look at what's going to happen as x goes to positive or negative infinity. And here we got to do something a little bit goofy, but not too goofy. So we're going to do our long division again and see that x squared minus x minus 6, if we divide it by the x plus 3, well, if we do this here, we'll multiply x plus 3 by x. That'll give us x squared plus 3x. Subtract straight down. X squared minus x squared is 0. Negative x minus 3x is going to be a negative 4x. Bring down our negative 6. Looking a little bit goofy here. Then we multiply by a negative 4. So there's going to be negative 4x minus 12. Again, we subtract straight down. And this is going to be negative 4x minus negative 4x, 0. Negative 6 minus a negative 12 would be a positive 6. And there's our remainder. So what we really got here is we're saying that x squared minus x minus 6 divided by, or is actually equal to the divisor times the quotient plus the remainder. X plus 3 times x minus 4 plus 6. Or, if we divide both sides by this denominator of x plus 3, so that now our expression looks like what we were looking at up here, now we see that this whole thing is equal to, so x squared minus x minus 6 over x plus 3, that's equal to, now we distribute this dividing by x plus 3 to both of these terms, and we're going to get x minus 4 plus 6 over x plus 3. And so as x gets really, really huge, the denominator in this term gets really huge, either positively or negatively. It doesn't really matter. But what that really means is that this thing right here, that's going to approach 0. Meaning it doesn't really factor into this at all. So what we're saying here is that this expression, x squared minus x minus 6 over x plus 3, is actually going to behave very similar to just x minus 4 as x gets really huge, either positively or negatively. So what we've really got here, this is what we call a slant asymptote. So we just do a quick little sketch here. I said we have a vertical asymptote at x equals negative 3. But now we have a slant asymptote of x minus 4. And so, here we go. What's going to happen as x is coming into negative 3 from the left, we're shooting off towards negative infinity right here. But now what's going to happen is the graph is going to turn around and get closer and closer and closer to the line y equals x minus 4 in that little area. Sorry, it's getting a little bit crowded. And on the other side, as x is approaching negative 3 from the right, it's going to shoot off to positive infinity. But then again, it's going to come around and going to turn around and then shoot off towards the slant asymptote this way. And so we can look at that on the calculator as well. Clear that out. So our numerator is x squared minus x minus 6 divided by the denominator of x plus 3. And we'll graph that thing. Okay, well, now we're seeing this part up here, but we're not seeing the other one. So let's zoom out a little bit. Or actually, we'll just go to window and change this up to, say, negative 20 to 20 on both of our axes. Oops, I totally messed that up. Ah, there we go. 20 I meant. And there, now we see it. This part of the graph is what we're looking at right here. And then this part right here. And we see the slant asymptote coming right through here, the line x minus 4. We could even put that in just to check. Yep, and there we see the line x minus 4. That's right there. So that's our slant asymptote that the rational function is getting closer and closer to as x gets really huge in either the positive or negative sense. And that's how to graph rational functions. We'll talk about it some more in class.